Hello, my name is Michael Dick, and I'm a Principal Research Scientist at Green Imaging Technologies, and welcome to this webinar. This is the second in a series of 3 webinars where I will discuss work we've done over the past year in developing spatially resolved wettability measurements using NMR. In this second webinar, I will go over how we employed the spatially resolved wettability measurements to track wettability as a function of position in some conventional samples. In order to test the spatial T2 based wettability analysis, 3 sandstone samples were examined. Pictures of each are shown here. Each was approximately 4 centimeters in diameter and about 5 centimeters in length, and each had a porosity near 15%. To get the 3 sandstone samples into states of mixed oil and brine wettability and saturation, the following workflow was followed. Briefly, we took samples that were initially clean and dry and saturated them with brine. We then centrifuged the samples at various speeds surrounded by dodecane to generate samples of mixed saturation and wettability, including some samples with saturation gradients along their length. Dodecane was chosen for initial testing as the oil because it has a simple T2 distribution, which makes wettability analysis easier. Finally, the rocks were dried to eliminate dodecane and water in them. Eliminate the dodecane and water in them, and then saturated to 100% with dodecane. T2 and spatial T2 distributions were then recorded for each step in the process in order to yield the data necessary for the T2 based wettability analysis. This slide shows all the NMR parameters employed for all the scans completed in this work, including the bulk measurements and the spatial T2 measurements. All NMR measurements were completed in an Oxford Instruments GeoSpec 2 Plus 75 rock core analyzer, like shown here, using a 43mm probe. Acquisition and processing of the T2 data was achieved via Green Imaging Technologies software. The wettability analysis of the T2 distributions generated by GIT software was then completed using MATLAB. This slide shows the 100% water saturated, 100% oil saturated, bulk oil, and bulk water T2 distributions. Also shown is the measured mixed saturation and wettability distribution following centrifugation of the 100% water saturated sample at 3000 RPM. It's shown here in brown. So now the name of the game is to mix the blue, the yellow, the green, and the red T2 distributions to give the brown distribution. As I mentioned in the last webinar, this is done by application of the forward model. This is the forward model's equation shown here, where W and H are the wettability distribution function, and H is the saturation distribution function. This slide shows the final saturation and wettability distributions in light blue and pink generated via fitting of the data shown on the last slide. So what becomes obvious now is how each measured T2 distribution contributes to the final estimated distribution once the model is applied. For example, if we look at the W times H times the 100% water saturated term, we see that from the 100% water saturated T2 distribution, there's only a small contribution shown here in dark blue. Conversely, if we look at the W times 1 minus H times bulk oil contribution shown here, we see there's quite a bit of contribution from the bulk oil T2 distribution. So overall, this data seems to indicate that following centrifugation at 3000 RPM, the rocks is mostly saturated with with oil, but is still water wet. This slide shows the contribution from each T2 distribution plotted on the same axis. The black line is the final predicted T2 distribution created by summing each of the predicted T2 distributions and applying some smoothing. So if you sum the yellow, the green, and the blue, and you apply some smoothing, you get the black. And as you can see, it agrees quite well with the measured distribution of mixed wettability and saturation shown here in brown. When the final wettability and saturation distributions are used, the water saturation is predicted to be 13.2% and the wettability is 0.888. So now that I've explained how we do the wettability analysis for the bulk data, I will now move on to the analysis for the spatial T2 data. This slide shows the spatial T2 data recorded for rock 109S following centrifugation at 3000 RPM. Both the stack plot shown here and the intensity plot are shown. This is the corresponding spatial T2 data for the bulk data that I just went over. So to complete the spatial T2 analysis, each slice in the spatial T2 distribution is analyzed individually for saturation and wettability in the same manner as the bulk data was. To do this, we employ the bulk oil and bulk water T2 distributions as before, along with the matching slices from the 100% water saturated and 100% dodecane saturated T2 distributions. This slide shows the results of the spatial T2 wettability analysis for rock 109S. The 100% water saturated rock was spun at 800, 3000, and 7500 RPM when surrounded by dodecane. The blue traces are the wettability predicted as a function of position from the T2 spatial T2 data. The data shows that the wettability is relatively constant irrespective of the saturation. The predicted saturation is shown in red. The wettability only begins to change when the saturation drops below 5% near the inlet face of the rock, following centrifugation at 3000 or 7500 RPM. To confirm the validity of our measurements, a second set of experiments were completed where water was replaced with D2O. This allowed the saturation profiles for each centrifuge speed to be measured independently, as D2O's NM are invisible. It should also be noted that because D2O is denser than water, the centrifuge speeds were reduced to match the capillary pressures employed with water. The saturation profiles measured via D2O shown in black for 800 and 7500 RPM and agree well with the predicted saturation profiles. However, unfortunately, there's no independent way to measure wettability as a function of position. However, the good agreement between the saturation profiles measured by D2O and predicted from our method gave us some confidence in our wettability estimates. This slide shows the predicted wettability and saturation profiles for rock 62A following centrifugation of the 100% water saturated rock with dodecane surrounding it at 1200, 3000, and 7500 RPM. Again, the blue traces are the wettability as a function of position in the rock, while the red traces are the saturation as a function of position. Again, the rock is water wet and the wettability changes very little with saturation. The black traces again show the saturation profiles as measured in a D2O experiment. In this case, agreement between the measured and predicted saturation profiles is not as good as it was for rock 109S, which I just showed. There's clearly an offset between the measured D2O measurement and the predicted saturation profiles from the wettability data. However, the agreement does get better as the centrifuge speed increases. This is more than likely a result of the T2 distribution becoming less congested as the water saturation decreases and the oil signal begins to dominate, and hence predictions improve because there's less overlap in the spectra. Finally, this slide shows the predicted wettability and saturation profiles for rock 96S following centrifugation of the 100% water saturated rock with dodecane surrounding it at 700, 3000, and 7500 RPM. Again, the blue traces are the wettability as a function of position, and the red traces are the saturation as a function of position. And the black traces are the saturation as a function of position as recorded in a separate D2O experiment. For this rock, the wettability analysis failed for 700 RPM. The predicted saturation profile, shown in red, looks nothing like that measured with D2O shown in black. The technique failed because at 700 RPM, the measured T2 spectrum is very congested, making it difficult to discern which T2 peaks are coming from oil and which are coming from water. The agreement between the measured and predicted saturation profile does improve for 7,500 RPM, however. Again, this is probably a function of the T2 distribution becoming less congested at higher centrifuge speeds, where the rock is saturated mostly with water. At both 3,000 and 7,500 RPM, the rock is predicted to be neutral wet. As I said earlier, the wettability as a function of position cannot be independently verified. However, the bulk or average spatial wettabilities derived from this fitting technique can be compared with wettabilities derived from other methods. This was done for rock 109S and 96S. By comparing the predicted wettabilities with those derived from both the Fleury's NMR method and an Ammont test. The absolute wettability values don't necessarily have to match for each technique, but wettability should be consistent for each method. For example, all the methods should be consistently predict that a rock is either oil or water wet. The 7,500 RPM data from our experience was chosen for this comparison both because it gave the closest agreement between the saturation profiles, this is the ones recorded with D2O, and gave the best quality of the least squares fitting. And in any case, all three of these methods, our method, the Fleury method, and the Ammont test, all said that both rocks were water wet. So thank you for tuning in to this latest edition of our webinar series on wettability. And if you have any questions, feel free to email us at info@greenmanimaging.com. Thank you.